algebra. So in today's lesson, we get to talk about objects being launched up in the air. Gravity's not affecting us, or wind, or a bird, or leaves, or anything. So in the last lesson, we talked about a rock being dropped from a building and things were falling. Today, we're going to be talking about objects being launched up in the air. Okay, this is really important because it reminds us that an object that travels at a constant speed can be described with a linear function. And it's going to familiarize us with a projectile context. Projectile motion. Oops, forgot to turn on my pen. Projectile motion. So let's read the opening paragraph. It says, a cannon is 10 feet off the ground. It launches a cannonball straight up with a velocity of 406 feet per second. So I've got the ground and a hill. We'll call it a cliff. So that's 10 feet. And a cannonball. So our velocity is 406 feet per second. Imagine that there's no gravity and the cannonball continues to travel upward with the same velocity. Complete the table with the heights of the cannonball at different times. Notice we are already 10 feet above the ground. My drawing is actually pretty stinky. Let's fix that. We're going straight up, right? So let's just do this table. Heights of cannonball at different times. So at time equals 0, we are at 10 feet. I don't want any more yellow, sorry. So time equals 0, we are at 10 feet. When time equals 1, we're going 406 feet per second. So 1 second would be 406 feet. But we have to add that to 10, so we're at 416 feet. And then time equals 2, so we did another 406 seconds. In 1 second, 406 seconds, we need to add that to what we've already traveled. $822, right? Our third second, we traveled another 406 feet. Add that to the previous distance we've already traveled. I am out of room on my table. They don't give me enough, etc. So we see what we're doing here. When time equals 4, it's another 406 feet plus the previous amount already traveled. You guys can totally use a calculator for that addition. I am not judging you. I can't see you. 406 feet plus the previous amount traveled. What's great about doing these tables, excuse me, is it's a great way to build the equation little by little. I can see my pattern. So I'm starting out with 10 feet and I'm adding 406 times t, right? So we have an equation, d equals, this goes right there. And then my equation is d equals 10 plus 406 times t. And then I tested a few times to make sure I did it right. So when t equals 1, I get 416, which is correct. When t equals 2, get your calculator out, I get 822, which is correct. So I always test out my equations. So moving on. Tracking a cannonball. Earlier completed a table that represents the height of a cannonball in feet as function of time in seconds if there's no gravity. This table shows the actual heights of the ball at different times. Compare the values of this table to those in the table you completed earlier. Make at least 2 observations. I'm going to write the values. I need to make it a little bit bigger. I'm going to write the values from the previous table below this one. So definitely 10. And for 1 second, we were at 416, 822, 1, 2, 2, 8, 4 seconds, 1, 6, 3, 4, and 20, 40. And our equation was D equals 10 plus 406t linear, right? So here we're comparing the values in this table with those that we completed earlier. Let's make 2 observations. So it looks like the table we made earlier is increasing faster, okay? Remember that was the cannonball that shot straight up. Great drawing, I know. The cannonball that shot straight up. So here the actual values, because we're now talking actual heights, are a bit smaller, okay, than the hypothetical ones. So this was hypothetical. We discounted gravity, remember? And you really can't discount gravity. It's a pretty important force. So the differences between the distance after some number of seconds is not constant. So if I do differences, let me get out a red pen. 400, the difference between 400 and 416 is 16. The difference between 822 and 578 is 244. Okay, 1228 minus 1084 is 144. Oh, I did that one wrong. Sorry, and I thought I said it wrong too. Oops, wrong marker. I can't erase the 244. 822 minus 578 is 64. Do you guys see any patterns? 5, 6, 3, 4. No, 1, 6, 3, 4 minus 1, 3, 7, 8. I'm subtracting those 2 numbers. 256. 2040 minus 1640 is going to be 400. Yep. So the difference between the hypothetical and the actual is actually increasing, okay? So that's interesting. Also, I want to point out the differences, if we go this way, the differences between the numbers, if we're trying to figure out if it's linear or not, is not constant. So we find that's not linear. If you do 400 minus 10, you get 390. If you do 758 minus 400, you get 358. If you do 1084 minus 758, 326. So the differences are decreasing. Okay, so not linear. We also can know that it's not exponential if we tried to find the factor. Okay. What else? I think that's it. Those are all the observations I can make. So let's plot the 2 sets of data we have on the same coordinate plane. You guys do this in your paper. I'm going to push pause and do this here. I'm going to make the hypothetical one in yellow. Okay, nope. hypothetical one is in yellow. That's hypothetical. And the actual one I'm going to do in blue, okay? All right, push and pause. Okay, there's my awesome graph. How are the two graphs alike? How are they different? I haven't seen enough, okay? They both look linear to me, even though I know they're not. The hypothetical, which is yellow, is linear. The blue is not. Hypothetical. So I know they're going to be different, but I don't have enough data to see it yet. So let's write an equation to model the actual distance d in feet of the ball t seconds after it was fired from the cannon. If you get stuck, consider the differences in the distances and the effects of gravity from a previous section. So we're actually going to look at the things I wrote in red up above. Look at the red numbers. We see here, these are all perfect squares. Okay, it's what we did in the previous lesson. Luckily, that may have just been today that you listened to it. So we know that it is, what we wrote in the previous lesson was 16t squared, right? So time is 1. 1 squared is 1 times 16. So when your time is 1, we use the 16t squared. When time is 2, it's 2 squared, which is 4. 4 times 16 is 64. So these values up here, if you look at the glowing dot, these values up here represent this part of the equation here, right? So we just need to equate for the difference. How to get to, we're trying to do actual, the 400. We know that 416 minus 400 is 16. 822 minus 758 is 64. Like, these are all the differences here. We just did some subtraction up. But when we're trying to find the equation, we have a little more work to do. But 16t squared is definitely a part of the equation. So let's go back to linear. Linear was yellow, and linear we understood. That was just distance equals 10 plus 406t, because that's what we did. So now for this blue actual, we just need to subtract everything that's written in red. So my distance is going to be my linear part. Super cool. The linear part of my equation minus 16t squared, because that is all of the stuff that is in red in the table. I need to subtract that away to get to the actual. It's a really fascinating way to build a quadratic equation. Okay, that wasn't easy. I don't want you to think that I'm like, yeah, that was easy, let's just move on. It's not. Okay, making those equations is pretty difficult. I know you guys can do it though. All right, moving on. Graphing another cannonball. The function defined by d equals 50 plus 312t minus 16t squared gives the height in feet of a cannonball t seconds after the ball leaves the cannon. What do the terms 50, 312t, and minus 16t squared tell us about the cannonball? Well, 50, just like the last one, was 10. That would be where it's being shot from, 50 feet above the ground. Okay, 50 feet from ground level. Um, 312t. If we think back to the linear one, that tells us the velocity, the initial speed of the cannonball. Cool? So that's our velocity. We could even be more accurate and say feet per second. And then the minus 16t squared is gravity. Remember, that was when we compared our hypothetical and our actual, that was the difference. So that's the effect on gravity pulling the cannonball back to the ground. Number 2 says use graphing technology to graph the function. Adjust the graphing window to the following boundaries. I would suggest open up Desmos and please practice this. I'm going to put it on the next slide, but practice is really good. So here I graphed this in Desmos and changed the window like it recommended. So observe the graph and describe the shape of the graph. It's a parabola. It's an unhappy parabola because it opens down, but it is a parabola. What does it tell us about the movement of the cannonball? We can say that as time increases, the cannonball increases in height until it reaches a maximum, and then it decreases in height. Right? This is parabolic motion, projectile motion we talked about earlier, but that is what we see here. We call that max. We can also say it's a peak. Maximum is a very mathy term that we're going to use quite a bit, but you can also say a peak. Let's see what else. Looks like the maximum is greater than, that's 1,500. So the maximum is higher than 15,000 feet. You know, maybe, let's see, 1, 2, 3, 4, not quite 16,000, or gosh, 1,500. Get my units right. It's over 1,500, not quite 1,600, 1,600. And then it hits the ground. The other thing that we see is, when does it hit the ground? If that's the time, it hits the ground at just under 20, was this seconds? Yes, seconds. So it left the ground at 0 seconds, actually just a little less than 0 seconds, which is odd, and it hit the ground at just less than 20 seconds. So these graphs tell us so much information, truly so much information, okay? What else do we need to answer? Yep, so these are all estimates. We're not really doing much. That last question that's not on this page says, what domain is appropriate for this function? Explain your reasoning. And you need to remember, because we've already talked about it, that domain is the x values. It's the input. In this case, it's the acceptable time. All right? So the equation's a good model for the height of a cannonball from the time it's launched. So our domain would be from the time it's launched at 0 seconds until the time it lands just below 20 seconds. Okay, so we would say our domain is 0 is less than or equal to t is less than or equal to 20 would be an appropriate domain. It really doesn't mean anything in the context. We just want to talk about our viewing window or what makes sense for the real life situation. Okay, that's actually it for today. Okay, part 3 is coming up.